Welcome to this lecture of the course. So, these two projections are very important in crystallography, orthographic projection and stereographic projection. Orthographic projection, certainly you all must be familiar, because that is simply projection of a point on a plane. So, if you have a plane, so that is the plane of projection. And then there is a point to be projected, then you simply drop a perpendicular from the point to the plane. Then Q is orthographic projection of P on the projection plane. So, that is the orthographic projection for you. We all know this. For the sake of completeness, I am writing this here, because this is the common projection which we keep doing all the time. And in crystallography, in international tables, which is one of our goals in this course, so you will find several orthographic projections. So, in the 3-dimensional crystal which we are interested in are 3-dimensional objects. So, let us say simple cubic. Simple cubic crystal. When we say simple cubic crystal, we mean simple cubic lattice plus one atom motif, and that atom is at the lattice point. So, the fractional coordinate is 0. So, you have a cubic unit cell, simple cubic lattice means lattice points are at the corners of the cube. So, in red I am marking the lattice points. They are still not atoms, they are simply points. When we say simple cubic crystal, then we will attach atoms to these points. So, and since we are saying one atom motif, so I will attach only one atom to each lattice point, and that atom I am placing at 0, which means with respect to each lattice point the coordinates are 0. 0 does not mean that one fixed origin, you place one atom at one fixed origin and be done with it, you will not get a crystal, that is not a crystal. So, 0 means these are coordinates with respect to each lattice point as origin. So, one by one you have to shift your origin and accept each lattice point as origin, and then place an atom there. So, when this becomes origin, I place an atom there, I place an atom there. So, essentially an atom at each lattice point. That is what is meant by atom at OOO. In the crystallographic language, motif atom at OOO means an atom at each lattice point, centered at that lattice point. So, this is a 3D cube with, and it is a simple structure. If you want to draw a projection of this, so suppose we select the base of the unit cell as projection plane, and we make an orthographic projection. So, since that base is a square, so in the projection it will look like nice square. Then 4 atoms are lying on the plane itself. So, they will be there. Other 4 atoms which are on the top surface of the cube. So, they will also project. You can see in the orthographic projection, they will project exactly onto these points. So, as far as projection is concerned, I will find nothing new. And if I am not writing anything as coordinates of these points, so x and y coordinate are visible. So, I have to label x and y. So, let us say this is x, this is y, and z is of course the projection direction, and z is going out of the plane, normal to the plane. So, the x y coordinates I do not write usually, that is the convention in crystallographic projection, because the x coordinate is visible, that I have gone all the way to the end of the unit cell edge length. So, the x coordinate is 1 for this atom, for example. Since I am on the x axis, the y coordinate is 0. So, x and y coordinate should be readable from the projection, but is usually not written. What should be written is z coordinate, but again the convention is that 0 or 1 z coordinates are not written, only fractional coordinates are written. So, if nothing is written in this projection, it automatically means that the z coordinates are 0, z is 0, nothing is written. And what is x and y? So, since this is my selected origin, then x and y for this is x is equal to 1, y is equal to 1. So, this particular atom, the full coordinate is 1 1 0. The z coordinate becomes z is equal to 0, and in the end I write nothing. I leave that to the intelligence of the reader, that they can just by looking at this atom, they can identify that this is a 1 1 0 atom. Usually, as I said, that in our convention for coordinates we will not use parentheses or anything. So, I just write it as 1 1 0. So, this is projection of a simple cubic unit cell. What about, this is only 4 atoms, I projected 8 atoms. So, other top 4 atoms are also getting projected there. So, z is not only 0 here, z is also 1, because 1 will also project exactly at that location. And if you really think of the entire crystal, so it is not only 0 1, it is also 2, because the next unit cell will give you an atom at 2 and then at 3. So, if you think of, it will have you the entire integer sequence 0 1 2 3, there is a unit cell below also. So, that will give you a coordinate minus 1, and then below that is minus 2. So, really this one single atom in the projection is a representative of the entire z row of atoms at integer spacings and integer coordinates. So, this is what is meant by an crystal orthographic projection. Why it is useful, you will soon see in the simplest example. In the simplest example of a simple cubic, it may not look so important. So, let us graduate to slightly more complicated. So, let us say body centered cubic. Body centered cubic structure. So, this is body centered lattice, that is Ci cubic I plus one atom motif, again that one atom is sitting exactly at the lattice point. So, O. So, if we now draw our cube, so again cubic I lattice. So, lattice points are now, since it is cubic, lattice points are obviously at corners of a cube. Corners are always lattice points in any unit cell, whether it is primitive or non primitive. And then since it is body centered, since it is I, there is a lattice point in the center also. And since I am saying one atom motif, so there is an atom sitting at each of these lattice points. Now, if you draw the projection of this again on the basal plane or the O1 plane, then like for the simple cubic, you will have 4 corner atoms, which as we have seen represent the entire row of infinite row of atoms at integer spacing. But this central one, the I centered, the body center one, will now project right in the center of the cube, center of this square. So, you will have one atom in the center also. And now, since it is not lying in the plane and not on the planes with integer height, so the height is not 0, 1, minus 1 or so, but height is half. So, now we will indicate the fractional coordinate only of this atom. So, as soon as I indicate fraction half here, we know that this is not lying on the projection plane, but at half height above the projection plane, obviously half height below the projection plane also by translational symmetry, because these fractions themselves are fraction in terms of lattice translation. So, 1 is a lattice translation, half is half the lattice translation in that direction, in the z direction. So, this also was not bad. So, next look at the face centered cubic. So, face centered cubic. So, face centered cubic structure. So, in this case there is a different name also which I suggest that you use. You call this cubic close packed, because we have another structure called hexagonal close packed and the two are related. So, to bring that relation out, to relate it to hexagonal close packed, this structure should be called cubic close packed structure. It is quite common to call it FCC crystal, but that is not a good name and it is not a good practice, and we will avoid that. So, we will not call it FCC crystal, we will call it cubic close packed structure, that is CCP in the short, and this is FCC lattice plus again one atom motif. At location 0, 0, 0. So, the lattice points now, since it is FCC lattice, we can also write cubic F. So, that means lattice points are at corners, as they should always be, but they are also in the centers of all faces. So, all the 6 face centers will have now lattice points. So, if we now draw the projection of this, so the 8 corners will project into these 4 locations, but there are 6 face centers also. This bottom face center is right on the face itself, but in the center. So, this is again at 0 height, but it comes there. So, there is additional point there, which was not there in simple cubic, and in body centered cubic it was there, but was at half height, but now at 0 height we have an atom there. The top face center projects at the same location. So, as we know that if there is an atom at 0, there is obviously an atom at 1. Now, the left face center, let us look at left face center, where will that project? At the left edge. So, it will project exactly there, and its height is half. So, since we have decided to indicate the z height is shown, because that cannot be read from the projection, unless and until somebody tells me that it is at half height or is at the same plane or at 3/4 height, I cannot know. There is no way of knowing for me, whereas x and y coordinate I can read, as I told you. So, that is why there is this convention that the z coordinates are always indicated. Similarly, the front face center, that will project here again at half height, the right face center will project there at half height and half height. So, this will look like the projection of cubic close packed. Now, let us go to still next level of complication, and let us consider what is called sodium chloride structure. NaCl structure. So, NaCl structure, if you see, this is cubic F. Now, for the first time you are going to see that motif need not be one atom, motif can be more than one atom. So, motif is 2 atom, let us say sodium, let us say chlorine at OOO or to be more precise chloride ion Cl minus at O and sodium ion Na plus at half OO. Now, how does that work? Let us see. And that is why, see, when I am saying the lattice, this is also face centered cubic CF. This was also face centered cubic CF. So, by lattice cubic close packed structure and sodium chloride structure or diamond cubic structure, all of them have the same lattice. So, lattice wise there is no distinction, but still they are different structures. Cubic close packed structure is not the same structure as sodium chloride structure just because they are both FCC lattice. That is why the reason to insist that the structure should not be called face centered cubic structure. Face centered cubic is a lattice and on that there can be different structures can be based. One example is cubic close packed, the second example is sodium chloride. So, where are the lattice points? Exactly again at the corners and at the face centers, top and bottom, left and right, front and back. Now, this is the skeleton, and I want to construct the structure out of it. So, I will have to start placing as per the recommendation of the motif. So, motif is chloride ion at OOO. So, I start putting the chloride ion at each lattice point, at OOO means at each lattice point. So, exactly like we did for the CCP structure. The back face center for me is now overlapping with others, but I can put it there. So, there are 14 atoms now. So, you can already see that now the 3-dimensional visualization of the structure by trying to draw a perspective diagram does not appear to be a very nice strategy, and I have only put chloride ions. I still have to put sodium plus ions, and when I start putting at the sodium plus ions, then I have to put them at half OO. So, with respect to any lattice point as origin, I go half along the x axis and put, I do not have to move along y and z axis. So, I come exactly at the middle of the edge. So, with respect to this lattice point, half OO is there and I place a sodium ion there. So, I put a sodium plus there. Then when I come to this lattice point, I put another half O. Now, with respect to this lattice point as origin, so my half O comes there. So, that is how I am generating this second sodium plus ion. I could have also thought of generating this by translating this ion by 1 unit along the y. This is also possible. We know that each edges of the cube are translation directions in those parallel to those edges. So, if there is a sodium there, translating it by 1 unit along the y axis, I should get a sodium plus ion there. But in the motif description, I am associating with each lattice point in turn. So, when I associate with this lattice point, this particular lattice point, then I get half O there. Similarly, half O with respect to each lattice point, if you start doing, you will get these. From this vertical, left vertical face will give you an edge center there, the right vertical face center will give you an edge center there, and the top face center will give you a ion there, and the bottom face center will give you an ion there. What about this back edge? Because there will be a unit cell there in the back, and the face center of that, when taken as origin and you move half O, you will exactly get there. So, actually you have an ion at all edge centers. That is what is the sodium chloride structure. If you can see the power of projection now, because if you now convert this into a projection, you will find that it is actually much neater and easier to understand. So, if I create a projection of this, the chloride ions at corners give me this, chloride ions at face center give me this, and 4 others here at half.
Will there be a sodium atom at the center of the
Sorry?
a sodium atom at the center of the unit?
Yeah, thank you, Harsh. So, this will come by attaching half O from this particular back face center, which I was missing. So, thank you for pointing that out. So, there is a, with the back face center, if I go half O, I exactly get in the center of the cube also. So, there is one atom at the center of the cube also, one sodium plus ion is at the center of the cube. So, now wherever you had ions at 0 height, you also have another ion at half height. So, now you have to be a little bit more careful by giving your z coordinate. You have to clearly indicate that which one is half. So, either by color coding as I am doing here, or by arrow, which also I am doing here, you have to clearly show that it is the blue one which is at half height and not the red one, because both are projected at the same location, because this one, this ion and the red ion will both project at the same location. Similarly, where you have half of chloride ion, there you have also at the base 0. So, this is 0. So, 0 we are not writing anyway, half we just want to make it clear that the half is for the red one there. So, similarly you can complete the projection. So, looking at this projection also, you should be able to construct your 3-dimensional unit cell. So, that is about orthographic projection and a sort of review also of what is meant by lattice and motif, and also an alert or warning that lattice is different from a structure. So, I have shown you 2 different structures, the cubic close packed and sodium chloride structure, both of which have the same lattice FCC. So, what is the distinction? Distinction is coming from the motif. CCP will have a single atom motif OOO, whereas sodium chloride will have 2 atom motif OOO and half OO.